Good afternoon, and thank you very much for having me. I appreciate the privilege to be able to talk about what I do, and I hope that you find my talk interesting. Again, I am Olalekan Oluwole. I am based in Nashville, Tennessee, United States, at Vanderbilt University Medical Center, one of the comprehensive medical centers in the United States. So these are my disclosures. So the learning objectives for today's brief talk will be a little bit of what are CAR-Ts, what are these things that are called CAR-Ts. It's going to be a brief introduction. We'll talk about select registration trials and their impact. We cannot talk about all the trials because the time would just not permit for that. And then the real meat of the discussion is the real world data and how we can use some of those data in patient selection. So what are CAR-Ts? I will define them briefly, talk a little bit about how they work and some of the side effects of therapy. So just general considerations. So a CAR-T is a stripped down version of the T-cell receptor. The T-cell receptor is part of how the body uses the immune response to target elimination of microorganisms and even malignant cells that the body sees as different. So the CAR-T process uses that method to target lymphoma or leukemia or whatever it is that they target. So the existing CAR-Ts can be chimeric or humanized. Chimeric because the part of the CAR-T that recognizes an antigen, it is reasonable to look at a chimeric or mouse model for that to be developed, but there are humanized constructs that are now in development. So the CAR-T has an extracellular antigen binding site that allows that CAR-T to recognize its target, and it retains intracellular signaling capacity that helps it to go through the metabolic changes that are required for the CAR-T to engage a target to eliminate it. So the figure on the left is a T-cell receptor. It is very complex. That is the natural T-cell receptor that all T-cells are made with. So the one on the right is the chimeric receptor. As you can see, it is a lot smaller because we do not have the technology to create a T-cell receptor complex right now, but we do not need all of that. We can get by with an extracellular domain, a hinge, and then an intracellular part that can make that T-cell to engage an antigen. So right now, the autologous human T cells, they are the CAR-Ts that are now being used to target cancer. All the approved products right now, they are autologous, and they are all second-generation CARs. And what do I mean by second-generation CARs? It is in this schematic. If you look, the blue part is the antigen-binding extracellular domain. The red part is the hinge. And what happens, how the T cell is able to stimulate itself is what tells us whether it is second generation. They do that through 4-1BB or CD28. So all the existing FDA approved products have their second generation CARs, and their co-stimulatory domain are through CD28 or 4-1BB. So we've gone through what our CAR-T is. Then I want to talk about select registration trials and their impact. For the sake of time, I will restrict this to large B-cell lymphoma only. So the first phase 2 trial in large cell lymphoma is the ZUMA-1. And as you can see, it was presented by Satva at ASH in 2016. It was the first one. And the schema was to enroll patients to relapse or refractory large cell lymphoma. They will receive those 2 million times 2 times 10 to the power of 6 CAR-T cells per kilogram. They will have fludarabine and cyclophosphamide to lymphodeplete. And the primary endpoint was the objective response rate. Of course, there were a host of secondary and other safety outcomes that were looked at. So the study met its primary endpoint. The objective response rate was met at 76%, really, really high, and complete responses at 47%. It, it was also clear to see that even in patients who had relapsed after autologous stem cell transplant, 75% responded to this, and almost half of those that were refractory to second line of therapy. This was the early report, and from the Kaplan-Meier curves, you can see that the responses are durable, although there were a few that did not respond. And many years out, the responses really appear to be durable. So the conclusion from Zuma 1 is that it met its endpoint. There were a few grade 5 events. Cytokine release syndrome occurred in the higher grade in 13%, and neurological events in 29%. The responses were durable. There are two other CAR-Ts that are approved. Tisangelacleucel, 93 patients, 52% objective response rate and 40% CR. Lysocaptogene maraleucel, 269 patients, objective response is only 3% and CR 53%. So taken together, these three CAR-Ts established the standard of care for third line setting. The question is, okay, if they are this good later on, how about earlier lines of therapy? And that is why I will talk about Zuma 7. I selected this. There are two others, but I just selected this. 359 patients is the largest of all the three randomized phase 3 CAR versus auto trials. So that's why I selected it. The eligibility is as shown: 180 patients randomized to Axicel, 179 to standard of care, with the event-free survival as the primary endpoint and other endpoints as stated. The study was clearly positive, and there were far fewer events in the CAR-T arm, and the likelihood of progression was much lower in the Axicel arm. So this is what led to the approval. Also led to other studies like the Lysocaptogene maraleucel is also approved for second line. So I think that should suffice for some information about registration trial. How about real world data? The largest that was first published was 17 centers. Actually, let me go back to this slide for a minute. There are merits and demerits, or there are issues with real world data. I want to talk about that for a minute. How do you get real world data? You can have a single institution series. It's relatively easy and quick to do that. The problem is that you're going to be limited in number, and because it's a single institution, you may just be able to do descriptive studies. You could do a multi-institution where many institutions can gather together and they can quickly come up with a number of cases, but the data will be a little bit limited because you're limited to what everybody is willing to share. But you could test a few hypotheses, and you have a lot more patients than one institution. There's also national registry body, CIBMTR. That is the largest sample of all, and it takes many times to curate that data for submission. So this one presented by Nastopil was 17 centers that just gathered together to do a quick report on Axicel post-marketing. The efficacy was ORR of 82%, very close to Zuma 1, complete response rate close to Zuma 1, and the EFS was, all of the outcomes were really close. The interesting thing to note was that even when 43% of patients were ineligible for Zuma 1, they still seem to have responded. So the summary was that it was as good as Axicel. Why was so many ineligible? What does that mean? You can divide ineligibility into multiple groups. Some are ineligible just because a lab point. For example, in a registration trial, a patient, if the cutoff is 75,000 for platelets, if a patient has 74,000, they cannot go on. But Is that 1,000 point different? Does that really mean a lot clinically? Probably not. But there are some other findings there, though, that we think are quite interesting. Like patients with a low ejection fraction, they were still able to benefit, and that is interesting to note. So the second real world data, which resulted more recently, was 260 patients from 8 US centers. They were able to actually look at axi-cell and compare a little bit to T-cell. T-cell means T-cell. 61 of the patients would have been ineligible for Zuma 1 and 43%, which was weird. And however, the efficacy seemed similar to what was observed in the registration studies. The safety data also showed that CRS was also high, or maybe even a little bit higher in the real world setting than in the registration studies. There are multiple reasons why this could be so. Some patients who may have not been eligible for a registration study because they are rapidly proliferative disease, they may be able to go in the post-marketing setting and they may have more side effects. The median time from apheresis to infusion, this is important. It was a lot shorter for axi-cell at 28 days versus 45 days for T-cell. And another important factor, outpatient therapy. 8% of axi-cell were done in the outpatient setting versus 63% of T-cell, and non-relapse mortality appeared similar between the two products. So the conclusion is that both products have similar outcomes as it was in the registration studies. Ineligibility for clinical trial did not really impact outcomes by much. There were lower CRS rates in some of the products, and we think they may be due to earlier intervention, because earlier on in Zuma 1, we were learning how to manage toxicity. By the time the real world data was coming up, treatment protocols have been modified so you could intervene earlier and probably present higher rates of toxicity. And more T-cell cells for sure were able to be treated in the outpatient setting. So I want to go through a few scenarios to talk a little bit more granular about patient selection. What are the things you need to do before you can choose a product? But before I go further, I want to make a disclaimer that neither axi-cell, nor T-cell, nor lysocell have been studied head-to-head in a randomized fashion. So what we are doing is looking at single-arm studies and making inferences which may not be strongly scientific based. However, there could be things to consider. So that is why I will say consideration, not recommendations, because these products have really not been tested head to head. So T-cells, if a patient is frail, you may consider T-cell in that instance. Why? Because CRS and neurological event rates might be a little bit lower with that product. So if a patient is more frail, they may be able to tolerate that. However, when you look at the objective responses, it tends to also be a little lower with T-cell. So you may want to also consider that as a possible trade-off. But the treatment you can give might be better than the one that you cannot give. Secondly, if a patient has rapidly proliferative disease, you know that you will have a shorter time to get the CAR-T manufactured for axi-cell than it is for T-cell for 28 versus 45 days in the real world setting. So you might want to preferably think about axi-cell in a patient with rapidly proliferative disease, because if you're waiting another 3 weeks or 2 weeks between the two product delivery might make the tumor so much larger that they may no longer be able to get it. So, however, if you had a very effective bridging therapy, it will not matter as much that you get one product later. CNS involvement is another consideration. The registration trial for tisagenlecleucel allowed treated CNS disease, whereas axi-cell did not. However, in the post-marketing real-world data, we have evidence that patients with treated CNS involvement might actually be able to get Axicel successfully. So both products have real-world data that suggests that once the secondary CNS lymphoma has been treated, remember, this is not primary CNS lymphoma. This is systemic lymphoma secondarily in the CNS. Once you've treated it, you can use either of the products, but there are more data with tisagenlecleucel. Relapse versus refractory disease. During the time that tisagenlecleucel was being tested, there were some manufacturing slot issues, so it lended itself more to patients who had relapse disease versus refractory because it took a longer time to get slots and so on. That was really not an issue with Axicel. In fact, they preferentially skewed the decision making to allow more relapse. I'm sorry, more refractory patients. So if a patient had refractory disease, you might want to consider Axicel. You could use this Axicel also, but it's one thing to consider. And outpatient therapy, we have real-world evidence that Axicel is more suited for outpatient therapy. I know I did not speak a lot about Lysocell. There are little real-world data with Lysocell. That is why I would not be able to comment more about it. But we look at Lysocell as somewhere in between Tisacell and Axicel. But the real world data is going to be coming forth with more publications subsequently. This is the end of my presentation. Thank you very much.